Okay, so on to part two. Questions at the end of this one will hopefully be a bit more meaty. Um, in the ramp up to that, I'm just going to go through a couple of them myself. Before we get to that, I have a question here which is taken from one of the examples we did in the previous session. So you've got two balls, again connected by a string, as shown there below. They're at rest on a smooth floor, and one of the balls is given an initial velocity in the direction away from the other, and when the string becomes taut, both balls start moving at the same velocity. Okay, and in the example from the previous session, we said that this has resulted in a loss of kinetic energy, and we had some specific numbers to work with, and we found what that loss of kinetic energy was. But what we didn't really address properly was why. Why has kinetic energy decreased? Before, when we were talking about collisions, one ball hitting another, or two particles colliding, or even an object bouncing or hitting a wall, we said energy could be lost because within the collision, the objects, they have some physicality. They compress, they heat up, they make a sound, they disrupt the air around them. That is how this kinetic energy has been transferred out the system. But in this case, I'd be interested to know what your thoughts are, because they haven't directly collided with each other. The floor is smooth, so forget about friction and that causing any sort of transfer or loss of energy. Why is it that when one of these particles, one of these balls, causes a jerk in the other using a string, that we could have a loss of kinetic energy? Have a think about it. Why might that have happened? You can pause. Okay, so the answer to that one, I'm going to confess. So I was considering this problem, and I didn't immediately know the definite answer. I had my suspicion. I tried to find it in the textbook. I gave it a Google, and I couldn't actually come up with a definitive explanation. So certainly a house point to anyone who can explain it properly. If you've had a similar question in physics, then they might have given you an explanation which might be satisfying to you. But I'll tell you what I believe is one possible explanation. As I say, if you can better me on this, point to you. I would say the string itself, if you imagine if you jerk a string, then what's actually happening, it's that you're almost causing some material damage to the string, right? If you imagine an elastic band, right? So set aside a fact, the elastic potential energy. You stretch an elastic band and it stores elastic potential energy, and you unstretch it and the elastic potential energy is gone again. So all is well. But as you repeatedly stretch an elastic band, you're almost distorting it and damaging it. It becomes stretchier and stretchier and stretchier. So it's almost like, I believe we're breaking the bonds or the physical connection between the material and the band. We're breaking it down to the extent where it's less capable of holding elastic potential energy. And even with a string, I think in the real world, when we have a sort of imperfect string, the jerking of those two balls will cause some sort of damage or stretchiness in the string. And even if it's effectively imperceptible to the point where the string is not changing length, there is still some sort of loss of energy to the environment. So that's my attempt at an explanation. Don't take it completely at face value, because, as I say, this was a really specific question and I couldn't seem to find anything on the topic of this one. I think perhaps that could just be because it's just taken for granted that almost any interaction between physical objects results in loss of energy to the environment. And so it may not be thought of as necessary to give every single possible interaction of objects and explain why you've lost energy to the environment. So to summarize, I think the best way, for sure, the one certainly correct way of saying what's happened is to say energy has been lost to the environment. So the environment is effectively anything outside of the system that we're dealing with. In this case, the two balls. So any energies associated with them are within the system. Any energies transferred outside are outside the system, and we would say they've been transferred out to the environment. So that's how I would phrase it in this case. Okay, so let's look at the first of our examples. I've decided to take examples that are actually just from questions in the textbook. In this case, because I feel like the examples in the textbook for this chapter, as I say, they're not quite meaty enough. They are mostly just applying formulas and plugging in the numbers, whereas some of the questions they give you are actually a bit more meaty. So to just bridge that gap, so I don't throw you necessarily straight in the deep end, I thought I'd just do a couple of the more meatier problem solving questions, so you can see some of the techniques you might use, and then from there you can try some of the questions yourself. So just two examples I'll go through. So this first one I quite like. You've got a train, its mass is 30 tons, and it's moving with a small speed, v, and that impacts upon a number of stationary carriages, each weighing 6 tons, but you're not told how many. The complete train and carriages now move forward with a speed of 5/8 v. Find the number of stationary carriages. So to just illustrate what's actually going on here, you've got this train track. No, I'm not even going to attempt to draw a track. You've got this earth with a track on it, and there's a train, and you've got some number of stationary carriages, we don't know how many, and they're just sitting there on the track. And what's going to happen is this train going at speed v is going to hit the beginning here and then push the whole system along as one. And that's our before and after. So I've drawn the before, and let's just underneath draw the after. So the after is that the whole thing travels as one single unit with one single mass that we can consider as one mass. So we're going to find the number of stationary carriages. Let's just mark on the remaining information. The initial speed of the train was v, and then the complete train and carriages are going to move with 5/8 v. The mass of the train, so the mass of this thing is 30,000. I'm just going to write 30k for now and literally define k as 1,000. And then the carriages each weigh 6k, 6 tons. Okay. And again, we don't know how many there are. Here we go. So perhaps what would make sense is, because we don't know how many carriages there are, and that's what we're actually about to find, let's give that a variable name. I'm going to call it n. So n is the number of carriages. The number of carriages. So let's consider the before and after situation. Before, or initial, what is our momentum? It's 30k times v. Right, because all the momentum is currently being, would you say, carried? It's currently associated with this train, and these carriages have zero momentum because they're sitting there at rest. And then after the train hits the carriages, you've got all of them together, and the new speed is 5/8 v, being multiplied by a mass of, in this case, 30 plus 6n times k, right? So 30 plus 6n, and then let's just stick the k in there. Okay, So then if we equate those, 30 kV equals 30 plus 6n times k 5/8 v. If you don't like my use of k, by the way, that's fine. It's pretty non-standard. I've just thrown that in there because I didn't want to write lots of zeros. We can get rid of the k, we can get rid of the v, which we weren't interested in the first place, and we end up with 30 equals 30 plus 6n times 5/8. And to just speed this up, I'm going to put 5 there and I'm going to put 8 here. So we get here 240 equals 150 plus 30n. Difference between 150 and 240 is 90. Divide by 30, we get n is 3. It's a whole number. That's a good sign that we've got the correct answer, because you can't have a decimal number of carriages. Okay, and that's it, number of stationary carriages. Cool. The fraction of the original kinetic energy lost in the impact. So a bit of a funny way of phrasing it, the fraction of an original kinetic energy lost in the impact, but just good to be aware of this type of question. It's not asking you for kinetic energy lost as an absolute value, rather the fraction. So that means what it's effectively asking for is the initial kinetic energy minus the final kinetic energy, and then divided by the initial kinetic energy. So it's almost the absolute value lost, but obviously you're going to have to divide by the initial at the end. Now, if you think about it, this makes sense as a question to ask. Why have they said the fraction of kinetic energy loss rather than absolute value? It's because we still don't know what v is. We have no idea what speed this train hit the carriages at. So if I don't know the speed, I can't possibly know how much kinetic energy was lost. But we can actually, and it makes sense to find the fraction, because as we'll see, the v is just going to cancel out. So it doesn't actually matter what speed it was going at. The fraction of kinetic energy lost is always going to be the same, regardless if the train was going at 1 meter per second or 1,000. It's still going to be the same fraction. So what was the initial kinetic energy? It was 1/2 times 30k mass times v squared. So I'm going to write that 1/2 30k v squared, and let's also just put it under the fraction as well. And I'm going to take away the final kinetic energy. So that's 1/2 times the mass. And what is the mass? It's 3 of these. I've actually drawn 3, haven't I? So the dot 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 is 0. There's 3 stationary carriages, so that's 18k plus the 30k gives me 48k. So we've got 48k. And then what's the velocity of the whole thing? It's 5/8. So 5/8 v all squared. Okay, and then a whole bunch of stuff is going to cancel out here. First of all, let's get rid of these halves. Let's get rid of the k's. And we get 30 v squared minus 48 times 25/64 v squared, all divided by 30 v squared. And look what cancels out now, the v's. The v squared, and v squared all cancels out. And we end up with 30 minus 48, so on and so on. And at this point, I'm going to use the calculator. And I get 3/8 exactly. And that's it, 3/8. So the kinetic energy we started with, we now have 3/8 of that left. 5/8 has been lost to the environment because of the collision that has taken place. And quite nice, isn't it, that it doesn't actually depend at all on the speed at which the the object was going. Cool. All right, one more question we'll do together before you do some yourselves. Okay, so in this question now, we're going from guns and cannons and that sort of thing. We're going to be looking at an explosion. We haven't looked at this before because in the past we've talked about two objects hitting each other and then traveling together. So it's like two becoming one, and the explosion is the reverse of that process. It's one thing becoming two, or in a real life explosion becoming many, many things. So let's take a look at this. The principle is still going to be the same in terms of kinetic energy and conservation of momentum. The thing with a collision, though, is that when things collide, you tend to lose energy to the environment, whereas with an explosion, it tends to be a reversal of that. The explosion has been caused by something. This object has been torn apart, and it's because energy was added to the system. You know, in the form of, it doesn't matter, some sort of explosive chemical or some kind of physical interaction has caused this object to break apart. So in this question, we're going to look at actually not kinetic energy loss, but kinetic energy gain. So we've got this particle of mass m. It's moving in a straight line with speed v, and then it explodes into two parts. One of mass a third m, and the other of mass 2/3 m. So it's cleanly broken into these two pieces. They continue moving in the same direction as before, but of course they're going to be going at different speeds, because if it was the same speed, then it's not an explosion, then it's just a crack, and the object is still actually one piece. So by virtue of being an explosion, these two separate objects are now going at different speeds, albeit in the same direction. So let's draw this scenario. So we've got before explosion, and we've got after explosion. And before the explosion, this thing of mass m is moving with speed v. Now v itself is a bit of an not unhelpful, but perhaps not the best choice of constant name here. It doesn't mean final velocity, right? It's just a velocity, and it's technically the initial velocity. Usually we take u as the before and v as the after, but in this case, for whatever reason, we've been told its initial speed was v. It then splits into two. We don't know which one's which, but it doesn't particularly matter. And they both as well have their own separate speeds. Now we aren't given what those are, but we do know they're different. So because we know they're different, we're going to have to give them different names. Suitably, let's call them V1 and V2. And then the bog standard V can refer to the initial. And additionally, we've got an increase in the energy of the system of 1/4 mu squared, where u is a positive constant. And again, I'm just going to point out this u is also an unhelpful naming, because by convention we tend to be talking about u as being initial velocity, v as final. In this case, u has nothing to do with velocity, or at least it's not representing an initial velocity. U is just a constant, some arbitrary constant in an expression that we've been given, and v is the initial velocity. And v1 and v2 are what we're calling the final velocities of the two separate objects. Okay, so we need to find this u and v, and this is the situation we've been given. We've been given a before and an after, and we've got multiple unknowns. We've got an unknown mass, and in fact we haven't really been told anything really other than the relationship between these two masses. And then we've also been told that the increase in kinetic energy. So two things. A ratio of masses and an increase in kinetic energy. So everything else is going to come from the fundamental laws of the universe. We're going to use conservation of momentum, and we're going to use conservation of energy. we're going to need at least a couple of equations to get enough information. Luckily, we've been asked to give our answers for V1 and V2 in terms of U and V. So that speaks to the fact that even two equations probably won't be enough to eliminate all the unknowns. But we should be able to eliminate, at the very least, the M, and we'll see where else we can get to. So let's write down our equations. Let's do conservation of momentum first, because that's probably the easier one. So initial momentum is mv, and final momentum in this case is a third m times v1 plus 2/3 m times v2. So then let's go down here and equate those. So we're going to have mv equals a third mv1 plus 2/3 mv2. Those m's are all going to cancel away. And then I'm going to multiply both sides by 3. So again, imagine I'm equating this to this. Divide by m, multiply by 3, and I'm going to get one nice expression here. 3v is equal to v1 plus 2v2. So that's our first nice equation that we're going to use. Now let's look at kinetic energy. So we've got our initial kinetic is going to be a half mv squared, literally, because m and v is what we've been told. And then our final kinetic is going to be a half times a third m v1 squared plus a half times 2/3 m v2 squared. So that's going to give us a 6th m v1 squared plus a third m v2 squared. So now these two in purple would be equal if no energy had been added or removed from the system. But we've been told there is this difference between them. It's half mvu squared has been added to the system. So from the initial, we're going to add this additional energy, and we're going to end up with this kinetic energy here. And from that, we can form an equation. I'm just going to remove this part here, and we'll work it out in this space. So we've got a half mv squared plus this a quarter mu squared, and that's going to be equal to all of this over here. So that's a 6th mv1 squared plus a third mv2 squared. Immediately we can see the m's are all going to cancel, which is often the case in mechanics, that the mass is not relevant. And then we've got a whole bunch of fractions here, which I think would be nice to cancel out. So we've got 2, 3, 4, 6. So it seems like 24 would be a good choice. Yeah, you could do it your own way, but I'm gonna multiply by 24 to get rid of all the fractions. So I'll get 12v squared plus 6u squared equals, and again, this v and u, they have nothing to do with each other. They don't relate. Unfortunate naming. 4v1 squared plus 8v2 squared. Oh, I overshot, actually. We could have just multiplied by 12, couldn't we? Because these are all even numbers. Rushed a bit. 12 would have been sufficient. There we go. Okay, so we've got these two equations, right? We've got this one here, and now let's just have a think. Is that sufficient to actually get to our answer? V1 and V2 is what we want. So here we have v1 and v2 and a v, but that's fine because our answer can be given in terms of u and v. And over here we also have v1 and v2, which are our unknowns, plus these u and v, which are acceptable. So this should be sufficient. Our two unknowns are v1 and v2, and v and u are just constants, which we don't mind if they stay or go. It doesn't particularly matter. We can give our answers in terms of u and v. So now we just need to think about what the best approach is. We're probably going to end up with a quadratic, aren't we? So this is more about, you know, do we try and be clever and lazy, or do we try and be slow and inefficient but safe? Either way, I think we're going to need some extra working space. So I think probably the best thing to do is we're just going to have to try and eliminate either the v1 or v2 by making v1 or v2 the subject here. Seeing as we have v1 by itself already, let's just go for that one. So we've got v1 equals 3v minus 2v2, and then let's substitute that v1 into here. Yeah, so v1 squared is going to be, oh, this is going to be quite long, isn't it? 9v squared plus 4v2 squared minus 6v2. Oh, sorry, minus 12v1 v2. Yeah. Ooh, okay, and then two of those, let's just get this out of the way. Two of those is going to be 18, 8 minus 24. Okay, we just need to keep sight of our goal. Our goal is v1 and v2. V and u are just numbers. So everything here is in terms of v2. That's good. We can now substitute that 2v1 squared here. So let's come up here now. We're going to have 6v squared plus 3u squared equals the 2v1 squared, which is 18v squared plus 8v2 squared minus 24v times v2, and then still we've got a plus 4v2 squared. Okay. So yeah, at this stage it can get fiddly. You just need to keep in mind u and v. We were told we can give our answers in terms of them. They are just numbers. So really, this whole equation is one variable, isn't it? It's v2. So let's collect everything together if we can. We're going to get 8v2 squared, 4v2 squared. That gives me 12v2 squared. And then what about the v2s by themselves? Oh, yeah, no, that's fine. That's v2 by itself, minus 24v of it, of v2. And then we've still got 18v squared, and then these ones are going to be negative, so minus 6v squared gives me 12, and then minus 3u squared, and all of that is equal to 0. Cool. Okay, this looks like a quadratic in the form we want, right? This is a number times the variable squared. This is a number times the variable, and this is all just a number. So it's a x squared plus bx plus c kind of form. Right. Does anything simplify? Well, we can definitely divide it by 3. So let's do that. For all the good it does. So I think now we just need to be brave and use the quadratic formula. If you ever feel I'm going through this too slowly, feel free, just go ahead and do it yourself, and then you'll be fine. You can skip ahead to the questions. Otherwise, stick with me and we'll try and finish this off. We're going to use the quadratic formula. So let's just label this so we don't get confused. That's B and all of that is C. Okay. So B squared, minus B, sorry, we're going to get 8V plus or minus the square root of B squared, 64V squared, minus 4 lots of A, which is 4, times C, which is 4V squared, minus U squared. And all of that is over 2A, which in this case is 8. Okay, and now we just have to hope stuff cancels. So we've got 8V plus or minus the square root of 64V squared, minus 4 times 4, 16, times another 4V squared, minus 64V squared. Yes, it's going to cancel. And then we're going to get 16U squared. And that's still all over 8. Okay, so we're going down a good path, it seems. That brings us to 8V plus or minus square root of 16U squared. Let's just jump straight into calling that 4U, all over 8. And this is looking good. That's V plus or minus a half U. Okay, we've got somewhere. So we've got that V2 is equal to V plus or minus a half U. In terms of which one of those we can take, the positive or negative, it's not immediately obvious to me, so I think I'm just going to keep both of them for now and see what we get for V1. So V2 equals this, one of those, and let's pick the simplest relationship we have between the two of them. I think I've rubbed that off, haven't I? Let's just bring it back. So earlier on down here we had V1 equals 3V minus 2V2. Okay. So let's take a look then. So V1 equals 3V minus 2 lots of V plus or minus half U, which gives us 3V minus 2V, and then minus plus half U, because we've got minus 2 times the plus or minus half U. Okay, that equals V minus plus half U, and that gives us V1. Hang on, that doesn't seem quite... sorry, yeah, the minus 2 times the half, that was just 1, wasn't it? Sorry, so it's just minus plus U, minus plus U. Okay. Great. So that is almost the final answer. Now we just have to figure out the whole plus minus situation. So let's have a good hard think about this. We've got our two new velocities, and it's either the first is plus and the second is minus, or the first is minus, second is plus. They're either both possible or only one of them is possible. Let's just note a few things we know. We know that U is a positive constant. Okay, so that we know. So you know what, I don't quite see it. I can't quite see that we can rule either one out, and yet, so on Physics Maths Tutor they give you the working for this, and they say because U is positive, therefore, this is their logic, they say because U is positive, that implies that we must take the positive value here. But I can't see why that would necessarily be the case, because U could be positive, but a very small positive number, and taken away from V, you still have V2. Ah, okay, it does make sense. So V2 must be less than V, right? Because otherwise you wouldn't have the... No, I take that back. Sorry, we can't say that because we've been given an increase of energy to the system, so perhaps both velocities have increased. Right, I'm going to leave it there rather than wondering out loud in the lesson. I'm going to say we've definitely concluded this. The textbook, or not the textbook, but the textbook mark scheme online claims that it's this. However, I can't see how you could conclude that only based on this information here. Another opportunity for a house point for sure, I think. If you can justify to me why we would choose this pairing rather than the other pair, then me and possibly the other students would very much appreciate it. And you'll get a house point. Okay, I think that's enough. That was a tough question, a lot of algebra there. Hopefully you watched that at some slightly faster speed on YouTube. Right, let's try some questions. Time for you to give it a go. Okay, it says 2 slides, but considering that previous question took longer than I thought it was, I'm just going to leave it at these 2 because that's already about 18 marks. That's plenty. So have a look at these 2. I won't bother putting up the second slide. First case, you've got smooth spheres colliding with each other, and you're talking about the loss of kinetic energy, and you need to show a certain relationship. And again, you're going to have to be careful about justifying your choice of solutions. So that implies there's going to be some sort of quadratic, presumably that one. And in the second case, you've got this situation where it's not objects colliding, but it's objects being jerked by strings. So a different form of collision, I suppose, but with a string enabling it. And again, they receive a common speed. Can you figure out what that common speed is? Can you figure out what kinetic energy was lost due to the jerk? So give those 2 a go. You can pause the video now.